Hello, I'm sure you have realized that the topic of gravitation has quite a few formula. So in this video, I'm going to give a quick summary of the formula in this topic. So we start with two large masses, big M's, yeah? So we say that there's a mutual gravitational pull between the two of them. And the magnitude of this gravitational pull is given by this gmm divided by d squared. Now what is d? D is the center to center distance, yeah? Let me repeat again, it's the center to center distance. So the gravitational force obeys the inverse square law. And in fact, at infinity, that means when these two masses are at very large distance apart, the gravitational pull will tend towards zero. Now, if we allow the gravitational pull to accelerate these two masses towards each other, then they will be gaining Ke at the expense of GPE. On the other hand, if these two masses are moving away from each other, then the gravitational pull will be slowing them down, so they'll be losing Ke while gaining GPE. So gravitational forces can result in an exchange between GPE and Ke, right? So the GPE of the system when these two masses are at a distance of d apart is given by negative g mm over d. So it's d, not d squared. And also there's a negative sign here, which says that GPE is always negative. Now this makes sense because at infinity, when these two masses are far apart, the amount of GPE is 0 joules. We have chosen the reference GPE to be 0 at infinity. As the two masses come closer together because of gravitational pull, they'll be gaining Ke but losing GPE, right? So if you start off from 0 joules and you lose GPE, your GPE will become negative. Now let's move on to the situation when we see a tiny m. Let's say we notice that this mass is experiencing a gravitational pull in this way, in this direction. So we say that, oh, this little m must be sitting in a gravitational field set up by don't know what lah, some other big masses. G, the gravitational field strength, is defined as the gravitational force per unit mass. So the force experienced by the tiny m would simply be m times g. Now if the little m is moved leftward against the gravitational field, then it will be gaining GPE. On the other hand, if it allows itself to be pushed in the direction of the gravitational field, it will be losing GPE. So to keep track of the amount of GPE this little m have, we create this concept called the gravitational potential. And the gravitational potential is defined as the amount of GPE per unit mass. So to calculate the GPE of the little m, you just take little m multiplied with the gravitational potential. Now let's talk about one big massive m. We know that a large mass like the Earth can exert a gravitational pull on all the little m's around it, right? So imagine that this big M produces a gravitational field around it. And the gravitational field strength at each position at the distance r from the center of big M is given by gm over r squared. So r is always measured from the center of big M. Note that the gravitational field strength also obeys the inverse square law. So at infinity, at a spot far away from big M, the gravitational field strength tends towards 0. Now again, this gravitational field will cause little m's to gain or lose GP as it travels from one spot to another spot. So we say that big M also produces a gravitational potential around it. And the gravitational potential is described by negative gm over r. Again, single r, not r squared. Again, there's a negative sign here, meaning that gravitational potential is always negative. Again, this makes sense because at infinity, at a point far away, we have defined the gravitational potential to be 0. And we know that as a little m moves towards big M, it's going to be losing GPE. So if far away is 0 gravitational potential, then nearer to big M will be negative potential. Now just to complete the picture, let's have the situation when we are looking at a big M and a little m. So the little m is going to experience a gravitational pull. Why? Because little m is sitting in the gravitational field of big M. So to calculate this gravitational force, we can do F equals to mg. Now m is the little m. G is the gravitational field of big M. So g is gm over r squared. Big M here. And then you realize the gravitational force is gmm over r squared. Again, as little m moves from one spot to another spot in the gravitational field, it's going to gain or lose GPE. Why? Because it's sitting in the gravitational potential that's produced by big M. So to calculate the GPE of little m, you can do m times gravitational potential. Little m, because we are calculating the GPE of little m. But the phi here is the gravitational potential produced by big M. That's why when you stick in the negative gm over r here, it's the big M that's sitting here. Anyhow, you get the final expression, negative gmm over r. Alright, so it's your turn now. So take out a piece of paper and run through these 4 situations. So what are the formulas that are typically used when we're dealing with 2 large masses, when we're dealing with one little m on its own, when we're dealing with one big M on its own, and when we're dealing with one big M and one small m? If you can write everything out on your own, it means you have understood everything. Alright, that's all. Ta-ta!